Hi everyone, my name is Mathias Nicolle. I'm the Design Office Mechanical and Thermal Team Manager here at Anywaves, and I joined Anywaves about 5 years and a half ago.
I'm Gautier Mazingue. I'm the RF team manager at Anywaves, and I joined Anywaves 8 years ago.
To me, to be a great space engineer, the first need is to be curious. The reason why being curious is important is because space is a multi-physics sector, and we need to be aware of all the disciplines that comes into the design of a space product, and that does not just stop to the field you are specialized in. In Anywaves, for example, we work in close cooperation between the mechanical and thermal department and the radio frequency department, since during the design phase of the product, these two fields are directly connected, and a simple thing that will be added in mechanical design, for example, will impact directly the radio frequency design and performances of our product. So this has to come with compromise because the two fields are often working in the opposite directions, and we need to find a common agreement on solutions that we select. And so as a mechanical and thermal engineer, you need to be curious about what goes on and what goes on in the radio frequency department, to be able to understand the constraints of the different fields and foresee it and implement them in the design.
As Matthias said, we have to be very curious of other disciplines. As an antenna engineer, you also have a lot of constraints linked directly to what you want to do, the function of your antenna, what it have to do, the radiation pattern, the frequency band, etc., and so on. And you have to do our black magic, because we are shaping an object to be able to transmit some data, which seems impossible in the first place. But we cannot just stick to this design. We also have to take into account where the antenna will be. I mean, first maybe on the satellite, but also the space environment, and all the during the launching phase also we have to be careful because of vibration, the thermal environment. When we work alone just with RF engineer, we make the best product, but they are just in our mind or in our computer, and we have to work with a mechanical and thermal guy, because that's the big difference between a concept and a real antenna operating in space.
To me, the biggest motivation comes from the challenge of this environment. Definitely, space is not a place to be as a human and as a product, since it's very severe. There are mechanical challenges from the rocket launch with lots of vibrations, of shocks, of mechanical constraints that will apply to the materials that need to resist to those loads. Then you get all the thermal aspects with the thermal cycling around the Earth when the product comes in the sun or in the shadow of the Earth or another planet. So thermal gradients and thermal fatigue of the products, lots of radiations coming from cosmic rays, and that can really impact the electronics of the product. What else? Atomic oxygen that will try to erode the surfaces of our products. So this is a really challenging environment to get a product to work in, and it's really thrilling as an engineer to take into account all these aspects in the design phase.
Yeah, it's what you said, and I will just add that you have this environment which is very complex, and you have only one chance because the product has to work during the whole life of the mission, because we cannot repair it on orbit. I would say it's a mix of like formal checklist, something very standard database that we can find with NASA or ESA database, but it's also a lot of unspoken rules on how to make a good product for space. It's a mix of both. We cannot say you cannot just rely on formal database, and you can also not just rely on rule of thumb or best practice.
There is this whole normative environment with ECSS, NASA, MIL standards that we have to comply to make sure that our products is in line with the expectation of the space sector. But still, I agree with Gautier. I would say that 80% of the problems can be solved in the design phase, and that comes with mental checklist, and that comes with experience as a space engineer, to be able to integrate all the constraints from the environment directly in the design, really early in the design.
Yeah, to anticipate it, because you will solve problems before they occur, and that's one of the biggest part of our challenge as a space engineer.
Well, I would say that I arrived when NewSpace was already taking off, so I did not get a great opportunity to meet the old space. But the main tendencies that we can see on NewSpace are mainly affecting the size of the platforms and the accessibility to space. So basically what this means is that the satellites are becoming smaller and smaller. When we get before big geo satellites of several tons, now we have like cube size satellites of a few tens of centimeters. So this impacts the miniaturization of our products mainly, and the constraints on volume that is often even higher than the constraint of mass, which could be a misconception since when you go to space, often you hear every gram or every kilo is worth 7,000 euros or dollars. But most of the time, the biggest challenge that comes with NewSpace is volume with smaller products.
I would not say it's the main trend, but it changed a little, because satellites now become a little bigger than we had in the previous years. We are now not talking about 1U satellites or 3U satellites. We are something a little bigger. We have now flat surface satellites. So now we have more space, because in space we want better performances, and everybody knows that if you want better performances, you need bigger surfaces. So now we just have to optimize performances in a given volume that is a little bigger, maybe, than it was 3 or 4 years ago. You cannot play solo, I think, in space engineering. I think it's literally impossible, because, as you said, it's a multi-physics discipline, and you have to work with others to get the best optimized design.